This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the problem solving cases and the case studies on module 3, so which is basics of discretization. So in the previous sessions, we have discussed these aspects in the first module, so which is conversion of the conservative form of governing equation to non-conservative form, and we have seen the types of control volume. And in the types of control volume, if the control volume is fixed in space, so what happens if the control volume is moving? So we had said it is non-conservative form. So with that, we had seen the first module. In the second module, we have discussed about the classification of PDE, and we have seen the calculation of elliptic Laplace equation, and we have seen diffusion equation, and we have seen the second order wave equation. Okay, so we have said that the elliptic equation has the Laplace equation, and for the parabolic we have the one-way diffusion, and for the hyperbolic we have a second order wave equation. Okay, so now we will be seeing about the module 3, so where we will use those equations, and we will discretize them for the different finite difference formulation. So here the problem is, so whatever the equations we have, so let's say, so the Laplace equation we will take the unsteady, so which is, let's say, d phi by dt plus, let's say, alpha, or you can take some k times, so we have dou square phi by dou x square plus dou square phi by dou y square is equal to 0. So for this equation, we need to solve it. This equation we need to solve it using explicit and implicit method. Okay, so this equation we need to solve using explicit and implicit method. So the other one, so the same what we have taken, let's say you have this dou phi by dou square phi by dou t square, so dou phi by dou t plus k into dou square phi by dou x plus dou square phi by dou y square plus dou square phi by dou z square, so is equal to 0. So we need to see basically 2D and 3-dimensional aspect using the explicit and implicit techniques. So this is for the so here in the space it is Laplace equation. Actually, it is a combination of the parabolic and the elliptic nature. Okay, so we'll take the first question. So and we will the first equation, and we will solve it using explicit and implicit technique. Okay, so before that, let's recall about how do we perform the discretization. So we know Taylor series of expansion f of x plus delta x is equal to, or you can take it as phi of x plus delta x, which is equal to phi of x plus dou phi by dou x into delta x by 1 factorial plus dou square phi by dou x square into delta x square divided by 2 factorial plus so on. We have this. Okay, so what we have done, so we need to calculate this term. So if you want to calculate this term, so we have rearranged. So therefore dou phi by dou x is equal to phi of x plus delta x minus phi of x divided by delta x. So this is, and plus order of the translation error. So this is what we have. So for this equation, we apply whatever the 1 and 2 we have. Okay, so here you can see this is dou phi by dou x. Similarly, dou square phi by dou x square also, like we will get from this formulation. So using this approach, so this is the initial step. So this is the initial formulation which we have. So using this approach, we are calculating. Okay. So let's do this. So what do we have here? So we have first dou phi by dou t term. So before that, so we are doing it for first explicit. So we'll take this. So for the explicit method, so we'll solve this equation, which is dou phi by dou t plus k into dou square phi by dou x square plus dou square phi by dou y square is equal to 0. So we will solve this equation using explicit approach. So how do we solve first? So for the time derivative term, so let us write down, since it is two dimensional, so basically it is 2D. The x will have index I, comma y will have index j. Okay, so this is what we have. Now, so how do we write this equation is, so we have phi of I comma j to the power of n plus 1 minus phi of I comma j to the power of n divided by delta t. So this is for the first term. So this one is for the first term of the equation. Okay, plus k into, so what do we have? So we have second order differential. So therefore what we do is like phi of I plus 1 comma j to the power of n minus 2 phi of I comma j to the power of n plus phi of I minus 1 comma j to the power of n divided by delta x square. So this is what we have. Next, plus other one. So we have this, since it is along x direction, so the I value is changing, j value is constant. Okay. Now, so what do we have? Same, phi of I comma j plus 1 to the power of n minus 2 phi of I comma j plus phi of I comma j minus 1 to the power of n divided by delta y square is equal to 0. So this is how we have framed the equation in explicit method. So here what is the value of unknown we have? So we will take all known terms here and other unknowns one side. So what happens actually? So here this phi of I comma j to the power of n plus 1. So this is the value which is unknown, which is equal to, so what do we have? So phi of I comma j to the power of n plus k divided, so k into delta t divided by delta x square. So this is what we have into, so phi of I plus 1 comma j to the power of n minus 2 phi of I comma j to the power of n plus phi of I minus 1 comma j to the power of n. So this one term plus k into delta t divided by delta y square. So into, so phi of I comma j plus 1 to the power of n minus 2 phi of I comma j to the power of n plus phi of I comma j minus 1 to the power of n. So this is the equation how we have solved. Okay, so you take a two-dimensional mesh. You take a two-dimensional mesh. So we take this point which is I comma j. So we take this point which is I plus 1 comma j. So we take this point which is I minus 1 comma j, and we take this point which is I comma j minus 1, and we take this point which is I comma j plus 1. So this I comma j point is actually influenced by four values. So which is I plus 1 comma j, I minus 1 comma j, we have I comma j plus 1, we have I comma j minus 1. So this I comma j point is influenced by four neighboring points. So this is what we have. So this 1 and 2, 3, 4. So these are the four neighboring points which are influenced. So to solve this unknown term, so initially we will know what is the value of this phi of I plus 1 comma j to the power of n, we will know. Phi of I minus 1 comma j to the power of n, we will know. Phi of I comma j plus 1 to the power of n, we value will know. Phi of I comma j minus 1 to the power. So these values are known actually. Initially we will know. Okay. So once we know that, we will calculate. So here, okay, if you take constant, this value is known, and delta t, so the time step. So let us take actually, so delta t as 0.05 seconds and delta y as 0.1 meters. So delta x as 0.1 meters. So when we take this and k is equal to 1, okay. So what happens actually, these values will substitute here. So when we substitute here, so we will get the numerical value, and initially these values will be known from the grid itself. So from that, how we calculate the value of phi of I comma j to the power of n plus 1. So this is one kind of approach for the explicit method. So additionally, what do we have? So we have one more dimension. So which is, so we'll see. So what is the equation we have again explicit for the to solve? So we have dou phi by dou t plus k into, so we have dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. So how do we solve this equation? So initially we have I comma j. Now one more term k has come. That's it. So that is the difference. So here what do we have? So we need to actually specify I comma j comma k. That is the difference. So we'll just rewrite and we'll get to know. So how? So we have phi of I comma j comma k to the power of n plus 1 minus phi of I comma j comma k to the power of n divided by delta t plus k into, so we have three terms here. So we have dou square phi by dou x square term, we have dou square phi by dou y square term, we have dou square phi by dou z square term. So how do we write this dou square phi by dou x square? So already we have written, but for the two-dimensional point of view, we will extend it to three-dimensional. So that is it. So phi of I plus 1 comma j comma k. So if you see the previous equation approach, so we have I plus 1 comma j. So here what is coming? Additionally we have k term. That is the only difference. So if you have one dimensional, you have only I term. So if you have two dimensional, you have I plus I, j and k. Sorry, I and j. So if you have three dimensional, you have I, j and k. So that is what you need to know. And here for the superscript n, so time will not change. So basically time has power n, so that n will be constant. There is nothing changes. So you will write as n plus 1, n minus 1. So those aspects you will write, but there is nothing change which comes from the space point of view to the time. Okay, minus 2 of phi I comma j comma k to the power of n plus phi of I minus 1 comma j comma k to the power of n divided by delta x square. So this is what we have. Next, plus k into, same what do we have? So we have to write for y term. So which is phi of I plus 1, sorry, phi of I comma j plus 1 comma k to the power of n minus 2 times phi of I comma j comma k to the power of n next plus phi of I comma j minus 1 comma k to the power of n divided by delta y square. Next plus k into, so we have the third term, so which is phi of I comma j comma k plus 1 to the power of n minus 2 phi of I comma j comma k to the power of n plus phi of I comma j comma k minus 1, so divided by delta z square is equal to 0. So this is what we have for the three-dimensional point of view. So the basic difference what we have here is, so if you compare this equation where we have, so here we have I comma j and we have two terms. Now in the three-dimensional point of view, so two-dimensional point of view, we have four terms which are dependency. So here for the three-dimensional point of view, so we have 1, so we have 2, we have 3, we have 4, we have 5, we have 6. So 6 terms are depending. So in turn, we can say that for one dimensional we have 2 terms depending. For two dimensional we have 4 terms depending. We have for the three dimensional we have 6 terms which are depending majorly for solving this term. Okay. So for the full form of momentum equation, you can see how complex it is. Okay, so this is what it is applied for the explicit method. So we will see for the implicit method. Okay, so whatever equations we have seen for the 1 and 2, so basically we have taken this explicit method, we have taken implicit method for the equations 1 and 2. Okay, so for the explicit method we have solved, for the implicit method we need to solve now. Okay, so take the equation again, so which is dou phi by dou t plus k into dou square phi by dou x square plus dou square phi by dou y square equal to 0. So here for the implicit, okay, for the implicit what do we have is, so the RHS term will change. The second term will change. The first term is unaffected. Okay, so we'll see how. So the first term, let us write here itself. So that will be phi of I comma j to the power of n plus 1 minus phi of I comma j to the power of n divided by delta t, which is again plus, so we'll write continuation here, k into, so the term which is changing is here, phi of I plus 1 comma j to the power of n plus 1 minus 2 phi of I comma j to the power of n plus 1 plus phi of I minus 1 to the power of n plus 1 comma j divided by delta x square. So this is what we have. So you can see what difference we had. So n plus 1 term has come. Next, plus k into same. So you have phi of I comma j plus 1 to the power of n plus 1 minus 2 phi of I comma j to the power of n plus 1 plus phi of I comma j minus 1 to the power of n plus 1 divided by delta pi square equal to 0. So this is what we have. So what is the change that we observe? So here you can see we have only one term which is unknown, n plus 1. So the meaning of n plus 1 is, so the value is at next time level. Okay, so that is the meaning of n plus 1. So when you take the n plus n, n is nothing but the initial value. So n plus 1 is nothing but the next value. Okay, or the n is initial, so which is at time t is equal to 0. N plus 1 is nothing but at time t is equal to 1 second. So if n value will change from 0 to 1, 2, 3, 4, so on, the simulation time stops. Now the difference between the explicit and implicit method here is, so here we have only one term which is unknown, but whereas for implicit method we can see that, so how many unknowns we'll calculate. So this is unknown number 1, this is 2, this is 3, this is 4. So this and this is common, this is 5 and this is 6. Total we have 6 unknowns for 2D equation and only one term which is known. Okay, so how do we solve? That is the question. The question what arises is, we have more number of unknowns, we have only one known parameter. Now how do we solve? That is the major important question that we need to answer. Okay, so now to solve these equations, what we need to do is, so we have calculated at I comma j location, that is equation 1. Okay, so if we take the grid, so this is the location of I comma j and this is the location of I plus 1 comma j and this is I minus 1 comma j. So what we need to do is, so we have to write how many grid points we have. For those grid points we have to write all the equations. Okay, so when we write all the equations, we will actually collect all the terms together and form in the matrix of A x is equal to B. So there all the coefficients are collected. That coefficient matrix whatever we have, we will invert and we'll get the value of x. So this is the standard procedure. How do we solve the implicit technique? So basically this is 2D. So let's see 3D, how many variables we'll get and how much complex we have. Okay, so this is what we have. So for the 3D, dou phi by dou t plus k into dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square we have equal to 0. So whatever it is, 1D, 2D, 3D, explicit, implicit you take. So the first term dou phi by dou t value will not change. Okay, so let us write here itself. So phi of I comma j comma k. So here previously what we have only I comma j, because 2D. Since it is 3D, we have phi of I comma j comma k to the power of n plus 1 minus phi of I comma j comma k to the power of n divided by delta t. Okay, plus now k into, so what do we have here? Phi of I comma, phi of I plus 1 comma j comma k to the power of n plus 1 minus phi of I comma j comma k to the power of n plus 1. This is 2 plus phi of I comma phi of I minus 1 comma j comma k to the power of n plus 1 divided by delta x square. So this is the one term which we have, plus k into, so the second term we'll write. Next, phi of I comma j plus 1 to the power of n plus 1. So here comma k minus phi of, 2 phi of I comma j comma k to the power of n plus 1. So which is divided by delta y square. So here the extra term which we will write here, plus phi of I comma j minus 1 comma k to the power of n plus 1, so which is divided by delta y square. So this is what we have. Okay, so this is extension of this, plus k into, so we have phi of I comma j comma k plus 1 to the power of n plus 1 minus 2 phi of I comma j comma k to the power of n plus 1 plus phi of I comma j comma k minus 1 to the power of n plus 1 divided by delta z square equal to 0. So this is what we have. So what we have here, so the major differences, so you can see for 3D, so we have how many unknowns, we calculate first. So we have 1 and so we have 2, so 3, 4, 5, 6 and 7. Totally we have 7 unknowns. Here only 1 unknown here. So you can see how much complex it is. So you take 2-dimensional or you take 3-dimensional. So whatever you take, so what happens actually? So the number of unknowns will keep on increasing. So for the explicit method, so what happens? It is straightforward. There is nothing more. So there is nothing like what is the complexity which arrives. So let us compare all the 4 things what we have done. Okay. So when you see the equation 1 and 2, so for the equation 1, when we applied explicit method, so we have straightforward, which is only one unknown, remaining all are known. So we can simply directly one input, like one equation, we can solve one time at a time. So this equation is not depending upon the other grid points. So that we need to actually take into account. So when you take one equation, so at location I comma j, so this grid point or this thing will not depend on the other grid points. So for the explicit method, so it's very simple and straightforward, where it is actually relating to the other problems. Okay, so where it is not relating to the other problems. So this equation is applied for I comma j, so there itself we can solve. So that is what we have. You take 2D or like you take 3D, so it's same. So there is nothing. So you have all the values are which are known values and which is not complex. But when you come to implicit, so you take 2D, what happens? You have total how many? So 1, 2, 3, so 4. Sorry, actually here you have 5 unknowns. 1, so you have 2, 3, 4, 5 unknowns. So total you have 5 unknowns here. Okay, so 5 unknowns here, and only one unknown parameter, one known parameter. So here what we need to do, it's not very straightforward. So when you derive or when you want to solve the equation at I comma j, so you have to solve simultaneously equations at I plus 1, I minus 1, I minus 2, I plus 2, j plus 1, j minus 1, j plus 2. So whatever the grid points are available in the mesh, at all the grid points you have to write the equation and collect together and form a matrix. This is for 2D just I'm talking. So that is what we have. At one grid point, let's say if you have 7 unknowns, at other grid point, let's say which are common in nature, let's say you have 6 unknowns. So the number of unknowns keep on increasing. So to solve one equation one at a time is impossible. So therefore we have to collect them together and invert the matrix. So here for the 3D, what do we have? So we have 7. So we have 7 unknowns. Okay, for 2D we have 5. Let's say for 1D we will have, let's say, 3. So 3, 5, 7. So keep on increasing actually. Okay, so here same, the complexity has still increased. So from this, what we have seen for the explicit method, solving the technique for any equation for the explicit method is simple. So one equation, one time we can solve. Solving equation for implicit method is very tough. So with this, like we have seen, so how to solve the equations for the explicit approach, and we have seen for implicit approach, where we can conclude that if you want to solve through explicit, so one equation one time you can solve it anytime. So there is nothing complexity. It's simple and straightforward given if you know the initial conditions. But for implicit, what we need to do? So for implicit, so we have to write down all the equations which are available at all the grid points. So therefore what happens actually? So you need to write down all the equations, you have to collect in matrix form, and then you have to invert that matrix. So this is how we solve the equations for the implicit approach. Okay. So we'll see the other numerical or the problematic cases in the other module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.